Hello everyone, this is Arpia Banu and my roll number is 19LS301005 from 3rd SEM MSc Christy Jayanti College and a faculty Manikantan sir. Today I'll be presenting on the topic agrostatic electrophoresis in page. Electrophoresis, it is a separation technique that is based on the movement of the charged particles in an electric field. The term electrophoresis was coined from a Greek word phoresis, which means being carried away, and electrophoresis means to carry away with electricity. It is a method of gel electrophoresis used in biochemistry, molecular biology, genetics, and clinical chemistry to separate the mixed population of macromolecules. It is a natural linear polymer extracted from just seaweed that forms a gel matrix by hydrogen bonding when heated in a buffer and allowed to cool. They are the most popular medium for the separation of moderate and large size nucleic acid. The principle is it separates the DNA fragments by size in a solid support medium. The samples are pipetted into the sample wells. It is followed by the application of the electric current at the negative end, which causes the negatively charged DNA to migrate towards the bottom end. The rate of migration is proportional to the size. Smaller fragments move more quickly and they end up at the bottom of the gel. DNA is visualized by including the gel and intercalating dye, that is ethidium bromide. DNA fragments take up the dye as they migrate through the gel. Illumination with the UV light causes the intercalated gel to fluorescence. The larger fragments fluoresce more intensely because they take up more of the dye. So this is a setup of the agarose gel electrophoresis. Coming to page, it is a subtype of gel electrophoresis whereby the normal gel is replaced by the polyacrylamide gels. Gels are made by free radical induced polymerization of acrylamide and methylene bisacrylamide. It is most widely used technique of electrophoresis. The principle behind is any charged ion or molecule migrates when placed in an electric field. The rate of migration depends upon the unit charge, size, shape, and the applied electric current. So it is represented as V equals to E into Q divided by F, where V is the velocity, E is the electric field, Q is the net charge, and F is the frictional coefficient. Electrophoresis through agarose and polyacrylamide gel is the standard method to separate and identify the biopolymers, since these both gel are porous in nature. So this is how we set up the page. So the steps are involved in this process. Sample preparation. This sample may be any material which has proteins or nucleic acids. The sample is mixed with a chemical denaturant, usually SDS for the proteins and urea for nucleic acids. SDS is an anionic detergent that denatures secondary and non-sulfide linked tertiary structures and applies the negative charge to the protein, whereas the urea breaks the hydrogen bonds between the base pairs. Heating the sample to 60 degrees Celsius promotes denaturation. A tracking dye may be added to the solution, which allows to track the process of the solution. So a second method is preparation of polyacrylamide gel. The gel consists of acrylamide, bisacrylamide, and a buffer with adjusted pH. The ratio of acrylamide and bisacrylamide can be varied, but it is generally about 1 part 35. Lower percentage gels are better resolving for high molecular weight, and higher percentage gels are needed to resolve smaller proteins. Gels are polymerized in this gel caster with a comb inserted to create the wells. The comb can be removed after the gel is polymerized. Electrophoresis. The buffers are used at the anode and the cathode may be different or may be the same. An electric field is applied across the gel, causing the negatively charged proteins or nucleic acid to migrate across the gel. from negative to the positive end. Depending on the size, each biomolecules move differently. The small molecule more easier fit through the pores, where the larger ones have difficulty. The gel is run usually for a few hours, and this depends on the voltage applied across the gel. Smaller biomolecules travel farther down the gel, while the larger ones remain closer to the point of origin. Biomolecules may be roughly differentiated according to their size, which depends mainly on the molecular weight under denaturation conditions, but also depends on the higher order conformation under native conditions. So this is how we load and we run the electrophoresis. A last method is the detection. Following electrophoresis, the gel may be stained. We use coercive Bilgene brew for the proteins and ethylene bromide for the nucleic acids, allowing visualization of the separated proteins. After staining, the biomolecules appear as the distinct bands within the gel. It is common to run molecular weight size markers of the known molecular weight in the separate lane. So, to determine the molecular mass of the unknown biomolecules by comparing the distance traveled. So, this is how the protein mixture gets separated. So, the applications are we use to measure the molecular weight, peptide mapping, and estimation of the protein size, protein subunits or the aggregation structures, estimation of the protein purity, and quantification, detection of the protein ubiquitination, comparison of polypeptide composition of different samples, analysis of number and size of the polypeptide subunits, and post-electrophoresis applications such as Western blotting. So these are my references. Thank you.